Today's video we are going to see the questions from analog electronics. This video is a preparation for technical assistant of HSFC and SAC location. Okay, so let us see the first question. In this video we will be seeing little bit higher end question because the maximum marks or the maximum number of questions is being asked from the analog electronics subject. So this subject is very important when going for any competitive examination, especially when we talk the case for technical assistant. In the last video, we have seen that maximum questions were asked from the analog electronics subject. So I've tried to including including maximum number of questions as various parts. Okay. So the first question is this: determine the change in collector current. That is delta IC is a collector current change due to change in base emitter voltage VB from 25 degree to 100 degrees Celsius. That is, when the temperature is changing from 25 degree to 100 degree, there is a change in VB, and due to this change in VB, what is the effect or what is a change in the collector current? For a silicon transistor with beta is equal to 100, beta is a current gate. Also it is being given that consider at temperature 25 degrees Celsius, VB is equal to 0.65 volt, and for temperature T is equal to 100 degrees Celsius, VB is equal to 0.5 volt. So we have been given the change in the base emitter voltage when various temperatures, that is for 25 degree and for 100 degree. So the temperature is actually changing from 25 to 100 degree, and the corresponding VB changes is also being given. Now we need to find the change in collector current. Okay, and also the circuit is being given to you. This is a common emitter connection. Base is the input, collector is the output. There are two resistors connected, one to base and one to collector. Okay, VCC is equal to 10 volt. Now how to approach this problem? This is a common emitter configuration. Okay, so we know that the base current, that is IB, is following a relation with IC, that is IC is equal to beta times IB. Okay, so this is a relation for common emitter configuration of transistor, that is bipolar junction transistor. And from this circuit or from this connection, what is the equation for IB? That is, what is the equation for the base current? Let us see. So here we know that the base is actually connected to a 250K resistance, and this is connected to VCC. So the current flowing through this resistor will be actually the base current, right? And what will be the value of current flowing through that resistor? Will be the change in potential difference by the resistance value. Current is equal to voltage by resistance according to general Ohm's law. So here, what is the voltage difference or what is the potential difference? One end is connected to VCC, one end is connected to the base emitter region. So here the potential is base emitter voltage VB, here the potential is VCC. So the difference is VCC minus VBE by RB. That is the value of resistance. So this is a very basic thing you need to do. In order to find the base current means the current flowing through the base resistance. It is a difference in potential by the resistance value. Okay, I'm telling you how to do it from the scratch without by hearting anything. You can approach the questions like this. Okay, so what is VCC? It is 10 minus VBE is, okay, actually we need to find, we need to find the change in collector current. So we'll keep this equation as it is. Okay, now what is the collector current IC? IC is equal to beta times IB. This is the common emitter connection. So this is the collector current. Now we don't need collector current. We need to find the change in collector current for the various change in temperature. That is from 25 to 100. What is the change happening? We need to find. So let us see. So I'm going to apply a delta here. I'm going to first write the equation in terms of the voltages. IC is equal to beta times VCC minus VBE by RB, right? So I'm going to find DIC by dt, that is the change in collector current with temperature, is equal to, beta is actually a constant, we can take it outside, we don't need to multiply the beta inside, because in the end also we need to take it outside. So I'm going to take it outside in the beginning itself. D by dt of VCC minus VBE by RB. Here again, if you see, RB is also a constant. It is a resistance value. It is not actually getting affected by the, it is a resistance value, so it won't get affected by the temperature. So I'm going to take that also outside by RB. Now, we are going to put this d by dt to inside this bracket, and inside the bracket there are two terms, VCC and VB. VCC is actually the supply voltage. Okay, so it is not being given in the question, and also in general it is not actually affected by the temperature. The temperature is making an effect only on the base emitter voltage as per the question. See here, at T is equal to 25 degree, VB is equal to 0.65, and at T is equal to 100 degree, VB is equal to 0.5. So the temperature change is actually making a change in only the base emitter voltage, not in the supply voltage. It is something which we provide, right? So we can remove that, and this will be a negative value because there is a 0. So d by dt of VCC will be actually 0. There is no change. So minus VBE. Okay, so we'll take the minus also outside, and we'll put this d by dt to VB. Okay, VBE. So this is the modified equation. I'm going to remove this so that you can see it more clearly. So dic by dt, you can also you can write it as minus beta by RB into d by dt of VB, because the only term which is actually getting affected by the change in temperature is the base emitter voltage. Now we are going to find what is the difference or what is the change happening to VBE. So the temperature is changing from T is equal to 25 degrees Celsius to T is equal to 100 degrees Celsius, right? At T is equal to 25 degree, what is the VB? It is 0.65. Then at T is equal to 100, what is the VB? It is 0.5. So when the temperature is actually increasing, the base emitter voltage is actually reducing. So this is a negative change. Okay, we can find that at T is equal to 25, it was 0.65. Then as T is getting to 100, or if it is that is made as 100, the potential or the base emitter voltage is actually dropping. It is reducing. So the change is a negative change. And what is the change? It is 0.5 minus 0.65. I hope this concept is clear. The change is actually a negative change. Okay, so it is minus 0.15, or you can write it as minus 0.15. No difference in that. Okay, so this is the d by dt of VBE. That is, if you take the change, d by dt means differential or a change. In VBE, you will get minus 0.15. So I'm going to substitute that in the above equation. So we can remove this and into minus 0.15. I think it is very clear. Now this minus and minus you can take, that is, you can cancel. Now all these things are known to you. Beta is 100. I'll substitute all the terms. 100 into by RB is 250 into 10 raised to 3. And if you solve it, you will get the value as 60 microampere is the value of, you can write this as delta IC. Just a change in notation. It is actually d by dic by dt. Okay. So what is the change in collector current? It is not the collector current. It is the change in collector current happening when the temperature is increased from 25 degree to 100 degree. And due to that change in temperature, the VB is getting affected. And in turn, due to this change in VB, the collector current is getting affected. And this much is actually the change in collector current. The next question is this. What is the output waveform V0, that is V out, what is the waveform for a sinusoidal input of peak to peak amplitude 4 volt? That is, we are going to give a sinusoidal input of amplitude 4 volt. Okay. Okay, so peak to peak voltage is 4 volt. We are going to apply. Assume Z1 and Z2. These are Z1 and Z2. Sorry, I forgot to write it on the figure. Z1 and Z2 are identical diodes with 4.7 volt. So this is the built-in potential or the turn-on voltage of these two Zener diodes. In order to turn on this Z1 and Z2, we require 4.7 volt. Okay, and R1 value is, R1 is the input resistance, it is 10k, R2 is the feedback resistance, it is 20k. So if you closely observe this, this is a op-amp circuit and it is a inverting op-amp because your input is connected to the inverting terminal. Okay, so there is an input resistance of R1 value which is 10k and there is a feedback resistance. And only difference is that there is a, in the feedback loop, there are two Zener diodes connected. That is the only difference from that of a inverting operational amplifier. Okay, so if you see that the amplitude of the sinusoidal waveform which you are applying is 4 volt and the turn on voltage of these two Zener diodes is 4.7. Since the applied voltage or applied waveform is having amplitude, that is peak to peak amplitude is only 4 volt, but in order to turn on the diode we require 4.7 volt. So during the positive half cycle, one of the diode will get forward biased, but it will be only short circuited or it is shorted, and the other one will be open circuited. Since the built-in voltage is not sufficient, since the applied voltage is not sufficient or equal to the built-in voltage, one will get open circuited in the positive half cycle, and in the negative half cycle the reverse will happen. That is, this will get open circuited, the other one will get short circuited. Okay, so what will happen? Anyway, this loop will be open during both the half cycles because of the one diode will be open circuited always during both the half cycles because the applied voltage is not sufficient to turn on the diode. Okay, so what will happen? Since this loop is open, there is no effect of this loop in the feedback, that is the connection of these two Zener diodes. There is no effect in this entire circuit and it will just act like that of a inverting amplifier. So if the applied voltage is greater than that of 4.7 means then there is a effect of that Zener diodes is happening. Okay, but here since the voltage, peak to peak voltage is lesser than that of the turn on voltage or the built-in potential of these diodes, one diode will be always open circuited. Okay, so this circuit will behave just as that of a inverting amplifier and the output voltage, the output will have the same peak to peak voltage, but only difference is that it will be the 180 degree shifted version of your input. That is, if you are applying the waveform like this, your waveform will be like this. If this is VI, this is V out. Okay, that is, there is a inversion happening because of the inverting amplifier's nature. Okay, so since the input is connected to the inverting terminal, your output will be inverted form of your input. Only that is the difference. The peak to peak voltage of input and output is exactly the same. There is no effect happening due to this Zener diode or anything. Okay, so that is the answer. The output will have a same amplitude of your input, but it is an inverted version. Approximate frequency of oscillation of circuit shown below. So this is a circuit shown below. First, in order to find the frequency, you need to identify what is this circuit. This is actually a Astable multivibrator. So you should be knowing all the multivibrators, monostable, Astable. For the case of a Astable multivibrator, you can see that it is not being triggered by any external inputs. It is a self-triggered circuit. It is used for various purposes, for generation of square waves. Everything we use there is a lot of other applications also for a Astable multivibrator. Okay, so there are two transistors. It is a self-triggered circuit, and in order to find the frequency of oscillation, that is the question. F is equal to 1 by 1.38 RC, where R is equal to 10K. The inner circuit will be generating the oscillations. That is for generating the oscillations we use this inner circuit, 10K, and there is a 0.01 microfarad. Okay, so you need to substitute the value of R and C in this equation as 10K and 0.01 microfarad. So I'm going to substitute 1.38 into 10 into 10 raised to 3 into 0.01 into 10 raised to minus 6. And if you solve it, you will get it as 7.246 kilohertz is the frequency of oscillation of this particular Astable multivibrator. So the only thing is that you need to identify that this is a Astable multivibrator circuit and this is the frequency of oscillation. F is equal to 1 by 1.38 RC is a frequency of oscillation equation. The answer is 7.246 kilohertz. It is required to design a class B output stage, that is class B power amplifier output stage, to deliver an average power of 12.5 kilowatts to a load of 4 ohm. The power supply is selected so that VCC is 5 volt greater than the peak output voltage. Okay, so we need to actually design the select the VCC according to the output voltage. Determine the power conversion efficiency. We need to find the efficiency. So let us discuss some basic equations before going into this question. The efficiency is given by power AC, which is the output power, by PDC into 100%. It will be a percentage value. So this is the equation for finding the efficiency. Also, the power you can write in terms of the RMS voltage as Vrms square by R, that is V square by R. It can also be written in terms of the current as IRMS square into R. That is, we also know that the general equation for power is V square by R, and also we can write as I square R. So we are taking the RMS value Vrms square by R and also IRMS square into R. We can use these two equations. Also, there is another relation between the peak value of voltage and current between with the RMS values, that is Vrms is equal to V peak, that is Vp by root 2. Also, IRMS is equal to Ip by root 2. So these are some basic equations you should know to answer this question. Okay, so let us start doing the question. First we need to select the VCC. For that we need to find what is the peak value, because it is given in the question that the power supply is selected so that VCC is 5 volt greater than the peak output voltage. So first we need to find what is the peak value of output voltage. Okay, there's a small correction in the question. The average power is not 12.5 kilowatts, it is 12.5 simply watts. There is no kilo. Okay, so let us start doing the question. First I am going to find what is the peak value of output voltage so that I can select what is a VCC, because it is been given that the power supply is selected so that VCC is 5 volt greater than the peak output voltage. So that first we need to find what is the peak output voltage. So I am going to use a relation PAC, that is output power is equal to Vrms square by R, that is relating the voltage with the power and resistance. PAC is 12.5 watts is equal to Vrms square by R is nothing but the load resistance, it is 4. So Vrms square is equal to 12.5 into 4. So Vrms will be square root of 12.5 into 4 is square root of 50. Okay, so this is the RMS value of output voltage. Now what is the peak value? We can use a relation Vrms is equal to V peak by root 2. So V peak will be equal to Vrms into root 2. So V peak is equal to, Vp is peak output voltage. Okay, so it is Vrms into root 2. Vrms is square root of 50. So square root of 50 into root 2, that is square root of 50 into 2, that is 10 volt is the peak value of output voltage. So we have obtained the peak value of output voltage. Now we can find what is the VCC, because in the question it is not given what is actually the VCC. What is VCC according to the question? I will read it once again. The power supply is selected so that VCC is 5 volt greater than the peak output voltage. So VCC is equal to 5 plus Vp Vp is obtained as 10. So 5 plus 10 is equal to 15 volt is the VCC. Okay. So we have obtained what is VCC now. It is 15 volt. We have obtained the value for peak output voltage. It is 10 volt. Now we need to find what is the value of peak current. That is, what is the value of peak output current we need to find. Again, we are going to use the power relation in terms of current. PAC, that is output power, is equal to I square RMS into R. That is I square R. So I RMS we need to find. So I square RMS is equal to PAC by R. So we'll get I RMS is equal to square root of PAC by R. I RMS is equal to square root of PAC is 12.5 by 4. We'll keep it as it is. Next, what is the peak current? Again, use a relation. I RMS is equal to I peak by square root of 2. So I peak is equal to I RMS into root 2. I RMS is already known to us. So into root 2 means you can put that inside the square root. Okay. So this is not RMS, this is a peak value. Okay. So this is the peak value of your current. If you solve this sum, you will get the value as 2.5 ampere. So this is the peak value of your current. It is output current. Okay, I am going to write it here, 2.5 ampere. IP is equal to 2.5 ampere. Now, we need to find the DC power, PDC. Okay, PDC is actually VCC into IDC. Okay, this is the input power or PDC. It is equal to VCC into IDC. So, for that we need IDC. We only have IP. So, IDC is equal to 2 by pi IP. This is a relation. So, if you don't know any of these relations, please note that. So, the DC current IDC is equal to 2 by pi I peak. We know the value of I peak. So, we'll substitute it. IDC is equal to 2 by pi into I peak, that is 2.5 ampere. We'll keep it as it is. We'll go for the final simplification. Okay, so now we have all the required terms. I'm going to write the equation for efficiency. Okay, now I'll remove this circuit because it is not necessary. We have all the values in our hand. So, efficiency eta is equal to output power PAC by PDC into 100. It will be a percentage. Okay. So, what is PAC? It is already given in the question. 12.5 watt by, what is PAC? It is VCC into IDC. What is VCC? It is 15 volt into IDC is written here into 2 by pi into 2.5 ampere. Okay, into 100%. This is the sum you need to solve to find the efficiency. This is the power conversion efficiency of class B output stage. Okay, or the power conversion efficiency of class B amplifier. And if you solve it, you will get it as 52.3%, or you can round it as 52% is the efficiency of this class B output stage. Okay. So the answer for this question is 52%. So these are the questions which I have included in this video. Analog electronics is very important when concerning with technical assistant examination or any competitive examinations because maximum number of questions are generally coming from this subject. Please do practice it maximum as possible. Please do practice variety of questions. I really hope that this video was useful for your preparation. If yes, please do give it a thumbs up and also share this video with maximum of friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.